My research group is broadly focused on quantum devices. Quantum devices are nanostructures that allow us to isolate single electrons, and we can look at the behavior of a single charge or a single spin. There's a trend toward making smaller and smaller electronic structures, and therefore we need to understand the fundamentals of how devices behave at smaller length scales and size scales. We've been working on developing a laser that emits microwave frequency radiation, but we're trying to do this on very small size scales and at low temperatures and low powers. I think the unique aspect of this research is that it really studies the process of lasing or masing at the most fundamental level. So it's the ultimate limit, basically how far down you can push in terms of length scales and current flows. A laser is a device that emits radiation in the optical range of the electromagnetic spectrum. A maser is a similar device that emits radiation in the microwave frequency range. To make a laser a maser, you need three main components. The first thing that you need is a cavity that traps light, and you can imagine light bouncing back and forth between two mirrors. The second thing that's needed is a gain medium. And in our device, the gain medium is very small. It has length scale on the order of 50 or 100 nanometers, and it's a semiconductor double quantum dot. The third ingredient that we need to throw into the mix is a voltage source or an energy source, something that actually causes the electrons to transit through the system. And at a more detailed level, the way the system works is that the semiconductor double quantum dots have discrete energy levels that electrons can sit on. And by hooking the system up to a battery, we can force electrons to tunnel between these levels. When the electron tunnels, it emits a photon, a microwave frequency quanta of light. That gets trapped in the cavity and bounces back and forth. And that further induces what's called the stimulated emission process, more photon emission events that kind of amplify the field and lead to the laser or maser action. This is really a one-by-one electron hopping, which is quite unique. A quantum dot is basically an isolated island of semiconductor material. And you can imagine, making the island smaller and smaller and smaller until it only has enough space that one electron can kind of live on it or occupy it at a time.
This is the actual maser device, and we put it here in the refrigerator.
This device behind me gets down to 8 millikelvin. That's just a little nudge above absolute zero. And the reason for needing this dilution refrigerator is that if you think about the aluminum frame that this cryostat's supported on, at room temperature, the atoms that make up this aluminum structure are really shaking around. And that's very disruptive to the quantum systems that we want to study. And the best way to deal with this vibration problem is just freeze everything out. Go to low temperatures, it slows the motion of everything down, and you end up with a very clean environment to perform the experiments in. One of the reasons that we got interested in this area of research is that these microwave frequency photons can be used to interconnect different quantum devices. Our quantum dot would allow us to make a quantum version of the circuitry that's used in a classical computer. The photons would be the links between these individual bits that do the computation. So it's this level of control that we have now that we can exert on these systems that I think is really exciting and takes us in a new direction in terms of future work.